Hi, my name is Sam. I'm a postdoc at the Institute for Astronomy, University of Edinburgh, and it's my pleasure to talk to you on behalf of the DESI collaboration about our latest DESI BAO 2024 results and its implications on neutrinos. Um, and the talk is titled Reaching the Limits. So DESI is located at the Mayal telescope, 4-meter telescope at Kitt Peak National Observatory, consisting of 72 participating institutions and 800 collaboration members. And our goal is to create the largest three-dimensional map of galaxies and quasars on the planet. And we are grateful to our sponsors and participating institutions. So how do we do it? The most important ingredient of DESI is clearly the instrument, which consists of a focal plane with 5,000 individually controlled robots that are able to reconfigure within few seconds and target individual galaxies and quasars to obtain their spectra and therefore the redshifts. So the focal plane is located on the top there, and here we show one pointing, and for 20 minutes during one exposure in dark time, we trace the galaxies and obtain 5,000 spectra. So we have been doing so for a while now, and this shows the footprint of and the tile pattern of pointing the telescope into the sky, and each circle you see here represents one exposure. And you see the footprint of the year one, the DR1 sample, which already just after 1 year covers an effective volume of 18 gigaparsec over h cubed, which is 3 times the SDSS effective volume, which was obtained during 10 years. So this really shows how amazing DESI is. This sample consists of 5.77 million galaxies and quasars, and additionally 460,000 Lyman-alpha absorptions. And we have this month we released the results from the first year of observations, but the 3 years of observations are also already completed. So this is also coming out very soon. So on April 4, we had this press release about the first results from DESI that make the most precise measurement of our expanding universe. We use the BAO method. So we take the sound horizon, which is an imprint in the CMB arising from the pressure waves, how initial density perturbations have traveled. And this leaves an imprint on the CMB. And we can really trace that in the galaxy distribution and really measure the sound horizon scale, the angular scale, and the parallel scale. So this amazing feature image created by Claire Leman, you can also find it on our Redbubble store. The link is in the slides. There's a poster also, or mugs, or etc. Claire even created a cake. I fear that's not part in the store, but yeah, it was an amazing cake. And here you can see on the sides are the correlation function measurements of the BAO, which you can also see in this slide. So we measured the BAO for all the DESI tracers, the bright galaxy sample, luminous red galaxies, emission line galaxies, and quasars, and the Lyman-alpha forest. We measured the BAO, the isotropic scaling, which depends on the parallel distance dh and the angular distance dm squared. And we also measured the anisotropy from the quadrupole of the correlation function. And this is shown in this lower panel here. And we have reported this hint towards a varying dark energy model parameterized by W0WA, the equation of state for dark energy. And if you would like to get all the information about that, I really recommend watching the video where Sesh and Andrea were interviewed by Sean Hotchkiss. I think this is a very good resource to get an overview of all the ingredients of the analysis, like the BAO reconstruction, the Lyman-alpha forest, systematic test, the blinding, fiducial cosmology assumption, etc. So I really point to that video if you would like to know more details. However, I would like to point out a few things about this dark energy, this hint towards evolving dark energy, which were frequently asked about. So first of all, this is not coming from DESI alone. So DESI alone is clearly consistent with lambda CM at the 1.5 sigma level. And only when we combine with Planck, it gets interesting. We see a 2.6 sigma deviation, but it gets even more. The trend even goes on when we combine with different supernova data sets. So this shows the case of combining DESI and CMB with Pantheon, Union 3, or DES year 5 supernova. And this gives a hint or a preference of 2.5 to 3.9 sigma in favor of W0, WA with respect to standard lambda CM. And also, I think it's important to mention that this trend even persists when we replace some of the DESI points by SDSS data points. In the paper, we call it DESI plus SDSS, but so you might think that this is like a combination of DESI and SDSS, but this is not the case. We don't combine these two surveys because it's very hard to estimate the covariance. So instead we do something, we just replace some of the data points from DESI with the SDSS data points. And you can see here that even in that case, we still that quadrant of parameter space is favored. And there's an up to 3.3 sigma preference for the W0, WA case. And let me also highlight that when I quote these sigma values, it's always obtained from the delta chi-square of the full log likelihood, interpreted with difference of degrees of freedom of 2, because we are adding two parameters, W0, WA, with respect to lambda CM. And just to highlight quickly, this is the comparison of DESI with respect to SDSS and other BAO surveys. So when we combine or when we replace, for this DESI plus SDSS data set, we basically get rid of the low redshift DESI points and replace them by the SDSS points at the same redshift range. But we keep the high redshift DESI points, which are very much more constraining than anything than any other measurement that has previously been reported in the literature. And the SDSS data points are actually similar or even a bit more constraining at low redshift than the low redshift DESI points. So that's important to know about the DESI plus SDSS case. All right, so now let's go back to the DESI alone constraint, which are now plotted not only in the as a residual, but here you see the full sample. You see the data points compared to the Planck prediction here with the dashed line and the gray band, and the lambda CM fit here. The WZWA fit looks like this, and you can clearly see that it's not only this outlier driving this preference for WZWA, but also the relatively low dV over the RD measurement of from all the LRG and BGS samples. So it's really a combined effect. All right, so let me now go into the main topic of this talk, which is about neutrinos and reaching the limits. So with DESI BAO, there are two things we can say about neutrinos. So first of all, we can combine with Planck and measure the effective number of neutrino degrees of freedom and effective. And the other thing is neutrino that we can constrain the neutrino density and the mass sum of neutrinos through their effect on the background geometry. Since there's nothing really new in an effective measurement, I will not talk about this here in the interest of time, but focus on the neutrino mass sum or neutrino density aspect. So this is the 1D posterior we get on the neutrino mass sum parameter. So from CMB alone, or CMB either with or without lensing, the upper limit, the 95% confidence level, I will always cite the 95% confidence level constraint, is of order 0.2. Now, if we combine it with the new DESI BAO data, we go very low, up to we actually find 0.072. considering now that we have also limits, we have also from neutrino oscillation experiments, we know that if neutrinos follow a normal hierarchy, the lowest number of the mass sum should be at 0.06. In case of the inverted hierarchy, it should be 0.10. So this upper limit we find at the 2 sigma level from DESI plus Planck is uncomfortably close to the normal hierarchy bound. So where does this come from? Let's consider again the data and the model comparison in lambda CM. So from the shape of these data points on this curve, we can constrain the E of z or h of z divided by h naught, which in lambda CM only depends on omega matter. And the normalization of this curve depends on h naught RD. So within lambda CM, these two, omega matter and h naught RD, is what's really constrained by BAO. So here you see a comparison between DESI, SDSS, and this combined DESI plus SDSS constraint on the h naught RD and omega m parameters. You can see that for omega m, they're actually very similar. It's all about a bit less than 0.3. But for h naught RD, they are quite, there is a small discrepancy there. And you can see that for DESI, the discrepancy goes in such a direction that there's less overlap with the CMB, with Planck+ACT. Now, if we allow to let the neutrino mass float, the BAO results do not change much. But what changes is that CMB now exhibits this geometrical degeneracy between the neutrino density and the Hubble constant. And this is simply because the CMB wants to keep the theta star fixed, the angular size of the sound horizon. At the same time, omega b and omega c are fixed, so there's only h naught and omega nu left over to compensate and fix the sound horizon scale. However, this degeneracy is broken. As you see by SDSS, if we would combine SDSS BAO with Planck, approximately here is where we would get a constraint on neutrino mass, which has been reported to be 0.13. Now, if we consider the DESI BAO data, we see that this 2 sigma preference is in this point of parameter space, and yeah, it's just how the contour is shifted, especially in the h naught RD plane. Just for completeness, the combined DESI plus SDSS, or if we replace the low redshift DESI points by the SDSS points, then we get 0.8082 electron volts. And this is the same thing, but in the different plot here, I show the neutrino mass sum and h naught. And again, you can see that DESI breaks this geometrical degeneracy, and that's why we get this low, very good constraint on the neutrino mass. Finally, here I also show a plot of what the actual model predictions for dV and dm over dh looks like. If we fix the neutrino mass to 0.074 electron volts, so this is excluded at the 2 sigma level from the DESI plus Planck data. And this model is the best fit to the Planck data if the neutrino mass is fixed to that value. And you can see that increasing the neutrino mass will lead to higher dV over RDH, which is lower h naught. And this is more and more excluded by the DESI low redshift data points here. There are a few caveats to that. First of all, I would like to point out that there's a prior dependence. So in all of the plots I've shown so far, we have always assumed that the neutrino mass can be bigger than 0. So we have no prior information on what the neutrino mass should be. And this leads to the limit of 0.072 electron volts. But as soon as when we impose a prior motivated by neutrino oscillation experiments, then we find that the 2 sigma limit is actually 0.113 electron volts. This means that if we assume an oscillation experiment prior on this neutrino mass sum, we do not exclude the inverted hierarchy. I think that's also an important result to show. And another thing is the model dependence. So as you can see here, once we allow for other parameterizations of the background cosmology, curvature, varying dark energy of state, and varying dark energy equation of state, then the omega m h0 rd constraints really broaden up with respect to the lambda CDM model. And a consequence of that is that if we take the varying dark energy model, for example, the lambda CDM bound of 0.072 is in case of only DESI plus CMB is relaxed up to 0.2 electron volts. So this means that there's clearly a model dependence as well in that bound that we cited. So just to quickly summarize, here you see all the aspects that I've mentioned, the different limits. So we have in our baseline setting, we find the 0.072, but the prior from oscillation experiments and the model dependence are able to relax this. But still, we are getting uncomfortably close to the physically allowed limit, or the limit allowed by neutrino oscillation experiments. And as an outlook, I would also like to point out that please stay tuned for the updates from the DESI RSD and shape analysis that is going to come out soon. Just as a reference, in a paper of mine 2 years ago from SDSS data, we found that shapefit plus CMB gives an upper limit of 0.082 electron volts. Also look out for other neutrino-related research by other DESI members at this conference. For example, there's Hernan Noriega, who's presenting the Phelps code and the improvements he's been doing on the neutrino mass sum. So that's a very interesting avenue, I think. So DESI year 3 is also coming soon. So stay tuned for that. And my final question to everyone, what do we do? Imagine that with year 3, we surpass the physically allowed neutrino mass limit. Yeah, what do we do? Can we say that if the neutrino mass bound is very low, does it mean that lambda CDM is wrong, or is there any other idea how we can test this? Thank you very much, and very happy to see you soon at the conference.